Okay, video 3, manometers. Manometer is just a term for a pressure gauge, and I don't know why they still teach this. The truth of the matter is pressure gauges are more digital now than they are analog, but the calculations for the analog manometers are still on the AP exam. I know they're still taught in college, so maybe they're still using them in college. But anyway, manometers and barometers are just two different types of pressure gauges, and the calculations that go with them are a little complicated, so we should go through them. Okay, this would be a science manometer. This is called a closed-end manometer, and the reason why it's called closed-end is because they've sealed the end of it and created a vacuum. And so there is no pressure here, no resistance. And so as soon as you open up this valve, the gas comes through and it pushes on the end of the mercury column and causes the mercury column to move. Now, how much it moves, what you do is you subtract, we're going to call this H final, the final height. In fact, I'm going to use lowercase h because we've used capital H for enthalpy in the past. And this would be the initial height. So you just measure the difference between final and initial, and then that gives you the pressure of the gas. So in a closed system, pressure of the gas is equal to delta H, the difference in the height in the manometer, and delta H is H final minus H initial, just like any other delta whatever. So second type of science manometer is an open-ended manometer, and in an open-ended manometer what you have is you have the pressure of the air above it, or the pressure of the atmosphere, pressing down on one end of the column. They call it pressure of the atmosphere. And you have the gas pressing on the other end of the mercury column. Now, if the gas is equal to the air pressure, the column doesn't move. But if the column moves, then you can compare the movement of the column to the pressure of the atmosphere in order to deduce the pressure of your gas sample. Now, I always show this picture because I always recommend to students, when you start learning to drive, one of the things that you should keep in your car is a pressure gauge for your tires. If you're having problems with the tires going low, it's good to have a pressure gauge. This way you can kind of keep checking to see if once you inflate the tires, if it was just a matter of expansion and contraction because of weather changes, or if there's actually a leak in your tire. A lot of the newer cars now have a pressure gauge built right in, so you have a pressure sensor that can tell you what the pressure of the tires are in the car at all times. I show this picture because this is an analog pressure gauge, and it would have the mercury, you can't see it there, in the silver U-tube shape at the bottom of the gauge. But I would get a digital one that lights up at night, because it seems to me, in my experience, the only time your tires start having problems when you're driving is at night, when you can't see what your pressure actually is. All right, so manometers, closed arm and open arm, both of them make use of mercury, so we'll measure the movement in millimeters of mercury. And in that U-tube, the height difference is related to the pressure. Now, I took this note directly from the book, Convert to Kilopascals. I said in the last video, you only convert to kilopascals if they require you to. Most of the time, they're going to have the pressure in atmospheres. For a closed arm manometer, then you just measure the difference in the height of the column, left side and right side of the U-tube. But for an open-ended manometer, you got to determine the pressure based upon which side the mercury is the highest. If the mercury moves towards your gas sample, that means the air pressure is greater than your gas sample. If it moves towards the atmosphere, that means your gas sample is greater than the air pressure. And like I said, if it doesn't move at all, then your gas pressure is equal to the air pressure. So in an open-ended manometer, you have three things that can happen. In a closed-ended manometer, the mercury always moves. But in an open-ended, you could have no movement, where the pressure of the gas is equal to the air pressure. Or you could have, again, where the column moves, where the higher height, the column moves from the atmospheric side towards the gas sample side. And in that case, the pressure of your gas is less than the pressure of your air sample above it, and you subtract delta H to get it. If you open up the valve and the mercury moves away from your gas sample, that means that your gas sample is greater than the air, so you write pressure of the gas is equal to your air pressure plus delta H. So really you have to determine what's going on with the manometer. All right, so we'll try a couple of these. Okay, let's do this one. Set this one up. Suppose we have a closed system. Again, we know it's a closed system. Vacuum means that you have closed off the system and you're not getting any pressure on that side. So this is a closed system. And suppose they said this was 614 millimeters at the top and this was 212 millimeters here at the bottom. What is the pressure of the gas? And we'll convert it to atmospheres. All right. So in a closed system, pressure of the gas is equal to delta H, which is final height minus initial height. And so this is a pretty easy problem. We can just substitute in 614 millimeters of mercury minus 212 millimeters of mercury. So the pressure of our gas is equal to 402 millimeters of mercury. And I said, let's go ahead in this one. Maybe they ask you to convert it, or maybe a multiple choice and the answer's in atmospheres. So we'll go ahead and convert this to atmospheres. There are 760 millimeters of mercury in 1 atmosphere. So the pressure of this gas is 402 divided by 760, and I get 0.528947 blah 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 3 sig figs, so 0.529. Right, so pretty easy. If they give you something like this, where we have an open-ended manometer, so we're going to need a little bit more information here. First of all, the pressure of the air. I don't know. Let's make something up. Let's make it 1.04 atmospheres, and let's say our height is 317 millimeters of mercury on the low side and 742 millimeters of mercury on the high side. So now we got to determine, how is the mercury moving? Well, the mercury is moving away from, I used yellow, not good. Mercury is moving away from our gas sample, which means that the pressure of our gas is greater than the pressure of our air. So let's set up an equation to deal with that. Pressure of the gas is greater than pressure of the air. So it's got to be pressure of the air plus delta H. And so now we can substitute in. We get, we have a units problem here, so we're going to have to convert one or the other. I would convert to atmospheres. So let's do delta H first. High side minus low side, and we can do that substitution. Minus 317. And that will give us 425 millimeters of mercury. And we're going to have to convert that to atmospheres to add it to 1.04 atmospheres. So we'll make that conversion. 425 millimeters of mercury. Multiply by a fraction. Get millimeters of mercury to cancel. And convert it to atmospheres. So 425 divided by 760 this time. And I get 0.559. All right, so now we just add that together. Let's do pressure of the gas is equal to our air pressure plus our delta H. And that gives me, with the proper sig figs, 1.60 atmospheres for our gas. Okay. Now let's try another one. All right, they got it in inches, so let's convert that to millimeters first. You don't have to do this at the AP level, you would have to, but they're giving us delta H here, and they're saying that delta H is equal to 6 inches, so I'm going to go ahead and convert that. So 6 inches, and there's 2.54 centimeters in an inch, so that gives me 15.24 centimeters, so that gives me 152 millimeters of mercury. Again, that would be given to you. I wouldn't ask you to convert from inches to millimeters of mercury. On this one, however, the mercury is moving from the atmosphere side to the gas side, which means that the air pressure is greater than our gas sample. So they would have to tell us the air pressure. So let's make something up here. Air pressure is, and I'm going to do it in millimeters of mercury just to save time. Let's say it's a low pressure system for the day, and it's 748 millimeters of mercury. You got some bad weather coming in or something. All right, so pressure of our gas is going to be less than the air pressure, so we're going to subtract delta H this time. And they were nice enough to give us delta H, so we can just substitute in 748 millimeters of mercury, subtract out 152 millimeters of mercury, and that gives me 596, right? Let me say 152, yes, 596 millimeters of mercury for my gas sample. And I'm not going to convert it to atmospheres because they did not ask me to convert it to atmospheres or kilopascal. I'm just going to leave it as millimeters of mercury. I guess I could convert it to inches, but I don't feel like it. And that's it. All right, what else we got here on this? We did that. All right, a barometer is a manometer specifically used to measure the atmospheric pressure. And remember, we said that with pressure with a liquid, it depends upon the height of the column. So if we calibrate the column correctly in our glass tubing, as the air pressure rises or falls, so will the mercury inside of that glass tubing. And then usually they report it in inches, so 29.92 inches. So generally when you hear a weather report, they'll say the atmospheric pressure is 30 inches and rising or falling, or 29.8 inches and falling. Again, it has to do with how high the mercury moves up the tube in the barometer. And the last video I'll make will be on temperature, so put that together shortly. Thank you very much, and I'll see you. I won't see you. I don't know. I'm thinking about doing some sort of Zoom meeting just to see your faces again. But anyway, thank you for watching. Thank you for watching. What the hell? Okay. All right. Old person. Okay. Come on. I want to hit stop. There.